I love it. Why? pH problem, just like the others, right? Those aren't too bad. But this time, we have a weak acid. All right, this is problem number 5. That's benzoic acid on the board behind me. That is a weak acid. How do you know that's a weak acid? Billy, really? Come on. It's not one of the strong acids. Those are the strong acids. It's not one of those. It's got to be weak. That's how you know. Okay. Here's what it wants. This question says, what is the pH for this solution? It gives me a Ka for the benzoic acid. Ooh, that right away tells me that I'm going to have an equilibrium situation. That right away tells me if I'm given a K value for an acid or a base, then I know, and Ka, by the way, Ka, because I went over those when we talked about those Ks. A lot of different Ks. This is, we're talking about Ka here, the K for the acid. Those mean I have an equilibrium situation. That's the arrows going both ways. If I were to show any of these, let's take HBr. HBr is a strong acid. How do you know? Because it's one of the strong acids. That is what my expression, my equation will look like. We will not have an arrow going backwards. Never, ever, 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 ever can a strong acid reform this stuff, because that's the definition of a strong acid. It doesn't. It forms this and it stays there. This is a weak acid, which means some of these hydrogens will come off. See, we're missing it. Some will do that. Most won't. It's weak, so most will not. We'll do a problem a couple of times from now to calculate what percent actually deionizes or ionizes for the weak acid. So most of it, however, stays together. But some do, some of the hydrogens do come off, and if you get extra hydrogen, you're going to have an acidic solution. A weak acid can form a pH that's pretty low. That depends on the concentration. Now, don't get this confused. This is important. Most people say, oh, well, it's a weak acid. I'll just drink it or sniff it. Weak acid. No, don't do that. I had a student, I was just about to name him because I remember his name. He did this. It was like 25 years ago. If you do something stupid in my class like this, I remember your name. I do remember his name, but I won't say it. You'll be out there in YouTube land. He likes the smell of vinegar. Acetic acid is what a vinegar solution is. The acid in a vinegar solution is acetic acid. So 95% water and 5% glacial, which is the concentrated acetic acid. So you mix that in, you make weak acetic acid. I had the concentrated acetic acid. So he says acetic acid, I love the smell of vinegar. I hate it. I hate the smell of vinegar. And I hate doing labs with vinegar, but I have to. I hate it. So he decides he loves vinegar. So I hear him, I'm dealing with another student, and I hear him off in the corner of my brain over here where the acetic acid is being kept. I hear him say, oh, I love the smell of acetic acid. And that just took me a second to register, and I went, no. But by then he had the beaker under his nose. Yeah, he never did that again. That was a little painful on the nostrils. Yeah. Because it's a weak acid, acetic acid. Like benzoic acid is weak. But if it's in a concentrated form, a concentrated weak can be brutal. Or you could have a strong acid like HCl if it's highly diluted. If you have it, 1 part per billion, then you could drink it, no problem. Okay. I hope I made my point. There's strong and weak, and then there's concentrated and dilute. If you have strong concentrated, whoa, look out. If you have weak dilute, you go, you're nothing. Let's do this problem. Why do I love this problem? Because we're going to set up an ice chart. Yes, you do. You remember, ICE. I told you they solve all world problems. You can solve everything in the world that's wrong with the world by ice charts, duct tape, maybe a little bit of beer. Okay, if you're 21. So why do I need an ice chart? Because it's an equilibrium problem, 1, and it wants me to calculate the pH. So if I want to do the pH, I'm going to need to know the hydrogen ion concentration at equilibrium so I can put it into the pH equation. I took those equations off. At this point, they're relatively easy, so you wrote them down somewhere. So we're going to use those pH equations when we go through all this other chemistry. That's why I said earlier, you got to know how to use the pH equations. I mean, they're pretty easy to do, and you can't do any of this stuff without knowing that. It's like knowing the mole for stoichiometry. Got to know your pH. Equations, how to use them. All right, so this is an ice chart situation. Why? Because it wants the concentration of hydrogen. How do you know that? Because I got to get the pH, and I can't get the pH unless I know the hydrogen ion concentration. Ice chart. Concentrations mean ice chart. ICE. I need the initial concentration of the benzoic acid. Aha, there it is, 0.1. 0.1 molar. All right, 0.1 molar. The initial concentration of this is 0.1. So we have this to start with 0.1, which means initially I will have none of this. Initially none of that. There are cases initially when we do have some of this, and we'll be getting into that. Actually, I think the last problem is going to be that. No, that's next week. Okay, never mind. Just moving on. Zeros for the initial concentrations of those products. Change. Over time, we're going to lose this. We're going to gain this. And we're going to gain this. Plus x plus x. Add the two numbers together. Add the two lines together. 0.1 minus x at equilibrium. X. 0 plus x is x at equilibrium. All right. Set up a K expression. Ooh, this stuff, yeah, we're going to need this stuff for a long time, people. You have to know how to do these. K expressions. Okay, I'll go real quick. K expression is when you have the concentration of product over concentration of it's an R, reactant. Okay? So, the K value for this was given to me. It was given to me in the problem as 6.5 times 10 to the minus 5, right? 6.5 times 10 to the minus 5. So that's my K value. So I'm going to put that in. 6.5 times 10 to the minus 5. Okay? All right. K is equal to the concentration of the products at equilibrium. Okay, at equilibrium, that's the E in my ice chart. X and X. Over the concentration of the reactant at equilibrium 0.1 minus x. That's x squared on top. And that x I'm going to make go away. Rule of 100, remember? Only one problem. One problem. I mean, it's not too far away. We're actually coming up to it not too far from now. That we will not be able to get rid of that x. Why can we get rid of that x? It's so small, it's insignificant. How do I know? Look at the rule 100. What was that again? You take the initial concentration, so the rule of 100, you take the initial concentration, and you divide it by the K value. So that's 0.1 divided by 6.5 times 10 to the minus 5. Do it, do it, do it. You won't, do it, do it, do it. You won't. Times the function. Exponent and divide.